Good morning and welcome to this Conservation Applied Research and Development, or CARD, webinar on the expanded scope of commercial boiler tune-ups. Thanks so much for joining us today. I'm Mary Sue Lobenstein. I'm the Energy Conservation and Research Planner at the Minnesota Department of Commerce, Division of Energy Resources, and in that role, I identify and analyze gaps within utility conservation improvement programs and coordinate and plan research to fill the gaps. The CARD program is a major tool of that work. With me today is Laura Silver, who is a Senior State Program Administrator at the Department of Commerce, where she reviews Utility Conservation Improvement Program triennial plans and annual status reports. Laura has agreed to help us out this morning and moderate our Q&A portion of the webinar. Our presenter today is Russ Landry from the Center for Energy and Environment. Russ is a Senior Mechanical Engineer at the Center for Energy and Environment, where he has worked on energy efficiency in buildings for 32 years. This work has included several research projects on space heating boilers and supporting programs that address space heating boiler energy savings in multifamily buildings. It's great to have Russ here today for the webinar. I have to say I've known him for the whole 32 years he's been involved in the industry, and he's a very fine researcher and knows a lot about the topic of this particular webinar. So we're really fortunate to have him today. Before we start, I'd like to go over a few webinar basics. All attendees will be in listen-only mode. We will answer all questions at the end of the presentation, but as questions occur to you, please type them into the Q&A box and send them to all panelists. Use the Q&A box instead of the chat box if you would, that would be helpful. We will do our best to answer all questions within the time allocated, but if we don't get to some, we will answer them after the webinar. And this webinar is being recorded and will be available on the department's website at a later date. The slide set from this webinar will also be available, and you can email me right away and I'll send it within a few days. This webinar is one in an ongoing series that's designed to summarize results from research projects that are funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of that fund is to help utilities in Minnesota achieve their energy savings goal. $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects help utilities with data to enhance energy efficiency program designs within their conservation improvement program portfolios. As you can see by this pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is the commercial sector and will showcase results from the development and field testing of a controls tune-up protocol that focuses on optimizing boiler system temperature and staging control settings. Now I'm going to turn it over to Russ to begin today's presentation.
I appreciate that introduction, Mary Sue, as well as the funding from DER that helps support this project, and also the interest of all of you that joined the webinar today. Note that while the expanded scope commercial boiler tune-ups was the official name of this project, we used commercial boiler control tune-ups as the functional name for the service when we were talking with industry contacts, and I'll also do so today to help clarify how the service is different from traditional boiler tune-ups and boiler tune-up programs. I'd like to start my brief overview of today's presentation by highlighting the project's goal, which in a nutshell is an overview of the project. The project's goal is to develop and field test an expanded scope commercial boiler tune-up protocol that goes beyond burner adjustments to provide a comprehensive review and adjustment of boiler temperature and staging control settings to increase energy savings. With this goal, you can see why we refer to the scope and expansion as commercial boiler control tune-ups to try and provide a clear distinction from traditional tune-ups that focus only on safety items and burner fine-tuning adjustments. Although we eventually hope to see the traditional burner tune-ups and the control tune-ups delivered as part of a larger complete boiler optimization service, this field study only looked at the savings from the temperature and staging control issues so that utilities could understand just how much additional savings could be achieved by expanding upon the current program offerings. Now that I've talked about what the project is in a nutshell, The rest of the presentation will dig deeper to answer the traditional questions of why, how, who, and what. First of all, I'll focus on the several reasons why we believe it would be worthwhile to expand boiler control tune-up services to address temperature and staging control optimization. The first reason is that there appeared to be opportunities to more fully capitalize on the long-recognized savings benefits of outdoor reset controls. Since the 1980s, boiler outdoor reset controls have been an important part of SIP gas programs, and I believe that it's worthwhile to provide a brief review of how boiler outdoor reset controls save energy. This diagram shows the temperature of the water that the boiler system supplies to a building on the vertical axis and the outdoor temperature on the horizontal axis. As the diagram shows, when the outdoor temperature is low, an outdoor reset control keeps the boiler system up at its winter design maximum set point, which for most traditional systems is around 180 degrees. Then as the outdoor temperature gets warmer, an outdoor reset control automatically reduces the boiler system temperature. As the heating load goes down, these lower boiler system temperatures can still provide adequate heating of the building. So some systems will also have an outdoor cutout or warm weather shutdown control that shuts off the boilers above a certain outdoor temperature that's shown on the dash line there. Use of the boiler outdoor reset and cutout control saves energy in three main ways. First of all, when a valve fails open, it doesn't overheat the space that it serves as much as it would otherwise. So if it's 40 degrees outside, 180 degree water might heat a space up to 80 degrees or beyond if something went wrong with the system. In multifamily buildings, such failed open valves often lead to people opening windows or having other comfort issues. Secondly, the second way that outdoor reset saves energy is that the lower boiler system temperatures limit the degree to which someone can intentionally heat a space above a normal room temperature. Again, using an example of either a school space or an apartment building, you can have someone controlling a local thermostat expect to be heating their space above 80 degrees all the time. Thirdly, the lower boiler system temperatures reduce heat loss directly from the boiler and the boiler system piping. Because of these savings, outdoor reset controls rebates have been virtually universal across gas portfolios, but the savings achieved long-term is very dependent on their settings. Unfortunately, the settings on outdoor reset controls are often far from optimal for a number of reasons, ranging from settings being left at factory defaults to contractors or operators using excessively high set points to either reduce the chances of getting any callbacks for underheating or to compensate for other problems in the heating system, like a valve being stuck closed. The second reason why we thought the time was right to add controls optimization to boiler programs is to help utilities respond appropriately to the market shift to condensing boilers. Over the last couple of decades, condensing boilers have come to dominate the market for boilers in new buildings and as replacements for existing boilers. At this point, they also represent at least about 1/4 of the existing commercial boiler stock in Minnesota. While traditional boiler tune-ups might not achieve as much savings in newer condensing boilers that have less drift over time and air-fuel ratios, the operating efficiencies of condensing boilers is very sensitive to the boiler system return water temperature and boiler firing rate to a lesser degree. This is in contrast to traditional boilers that have very little change in operating efficiency as the boiler system temperature and boiler firing rate change. While condensing boilers continue to gain in market share due to their high rated efficiency, the actual savings realized can vary greatly because unlike most natural gas-fired equipment, the operating efficiency changes with operating conditions, as I said. This chart shows how condensing boiler efficiency improvements over conventional boilers can vary. The top red bar is for a typical conventional boiler, and the green bars below that show the actual operating efficiency of a condensing boiler and how it can vary from the maximum at ideal rated efficiency conditions to a minimum at higher boiler system temperatures. All the condensing boilers can achieve savings of 5 to 15% beyond what conventional boilers will provide. The specific amount is dependent on the operating conditions at the site. This is because much of the potential efficiency benefit of condensing boilers is associated with the extra heat captured when a portion of the water vapor generated by combustion is condensed instead of lost out the vent. And it needs to have the best operating conditions for that to condense and to get the maximum amount of condensing. This set of efficiency curves is for one make and model of condensing boiler, and this shows just how sensitive boiler operating efficiency is to operating conditions. The boiler efficiency is shown on the vertical axis, while the boiler system water temperature returning to the building to the boilers is on the horizontal axis. While there's little change in efficiency from the boiler water temperatures above 130 degrees, there are dramatic increases in operating efficiency when the temperature of the water coming back to the boiler drops from about 130 down to 180 degrees, or down to 80 degrees. I mean, this efficiency sensitivity to return water temperature is the single biggest factor in the operating efficiency of a condensing boiler. This increase in efficiency at low boiler return water temperature further enhances the saving that's achieved when outdoor reset control is used. Besides just reducing the boiler system load, you're also increasing the efficiency of the boiler itself. This graph also shows the moderate efficiency gains that can be made by operating condensing boilers at lower part load conditions. The bottom green curve is for a boiler operating at its full load capacity, while the two higher curves reflect higher efficiency realized when operating at 50% and 25% capacity respectively. The lower firing rates achieve about a 1% efficiency gain when the return water temperature is low enough to be well into the condensing range. The next answer to why we carried out this pilot was that a recent CARD-funded study suggested that for commercial condensing boilers in Minnesota, making adjustments to boiler control settings alone can provide substantially more savings than the burner air fuel ratio adjustments that are done as part of traditional boiler tune-ups. This chart shows the relative amount of savings that the previous study found could be achieved through various improvements to existing boiler systems. On the right-hand side, the combination of the blue and red slices show that temperature and staging control improvements were estimated to represent more than half of the possible savings. On the other hand, the orange slice in the bottom left for the burner tune-ups, which is what traditional boiler tune-up programs are focused on, were estimated to only capture about 1/6 of the possible savings. Therefore, enhancing boiler tune-ups by including controls optimization appeared to have the potential to dramatically increase the per participant savings for boiler tune-up programs when condensing boilers are encountered. And the last reason for the why we focused on boiler temperature and staging control adjustments was because of the potential to piggyback on the sales and delivery channels that are already being used successfully for burner tune-ups. Although the pilot results discussed today are based on hand-selected technicians performing only the control tune-ups, the eventual aim is for a full-scale program to have both the burner and controls tune-ups performed by the same technician during a burner tune-up visit. This would allow the expanded scope of services to reach the population of existing burner tune-up program participants and reduce the controls tune-up cost even below what was reported today in this study. Now that I took a shot at answering the why question, I'll move on to summarizing how we developed and field tested the controls tune-up protocol and who was all involved in this. We started by carrying out a market study that involved discussions with 21 local boiler industry contacts and a review of the state's boiler and pressure vessel inspection list, with a focus on hot water heating boiler systems in Minnesota that has input rates of 750,000 BTU or higher, and that focus was based on the inspection list. Besides talking with local contacts about the market statistics, we also asked opinions about many aspects of the controls tune-up service to help guide its development. These contacts included manufacturers' representatives, contractors, recommissioning providers, BAS contractors, end users, and distributors, as well as utility program representatives. After the market study provided very encouraging results concerning contractor interest and market potential, we undertook a protocol development process that involved many iterative steps taken in cooperation with local trade allies. In addition to the 4 contractors that carried out the controls tune-ups, We got feedback from a number of manufacturers represented as multiple times during the development and implementation of this. The latest protocol that will be available in the final report includes refinements completed during and after the 17 field site visits, as well as subsequent follow-up interviews with the servicing contractors and other trade allies. For testing the field protocol, we targeted different categories with among seven different site characteristics. These categories were prioritized to be representative of the most common variations within the Minnesota market, as indicated by the market study results. The two highest priority characteristics of building types and control were closely related. We focused on schools and multifamily buildings. Nearly all commercial boiler plants have their detailed individual boiler staging dictated by a local boiler controller in the boiler room and these local controllers are capable of using an outdoor temperature sensor to carry out their own outdoor reset control. In multifamily buildings, this local controller carries out the outdoor reset functions via local programming and is kind of self-sufficient. But in schools, the outdoor reset programming is generally implemented as part of the programming of a building automation system, or BAS system is indicated on here, that controls all of the HVAC systems in the building. This BAS system then passes a simple boiler system supply temperature set point to the local boiler controller. And then that local controller in turn coordinates the staging of the individual boilers to meet that set point. In order to find the appropriate mix of sites for testing the protocol, we first recruited boiler service contractors. Then these contractors recruited from among customers that they had an existing relationship with, including having some knowledge of their boiler systems based on past servicing work. These recruiting efforts provided a pool of 32 buildings, and the 17 sites that underwent the boiler control tune-ups were chosen from among these buildings. The highest priority categories were reached, at least the three highest. However, we did fall slightly short of sites, within the specific categories at the third through the fifth priority characteristics. The most notable deviations that we weren't able to recruit any appropriate buildings with only one boiler, and we were one building short of our target range for two different key boiler makes that are very common in Minnesota. However, overall we came very close to what we were targeting, with the targets met for 15 of the 19 categories within these 7 different characteristics. The final sites included 6 multifamily buildings and 11 schools, and all of these 17 buildings had condensing boilers. For these 17 sites, we carried out long-term monitoring for about a year before performing the boiler tune-ups in February of 2020, and continuing monitoring for periods ranging from a few months to 1 year. Because of the dramatic impact that the boiler system temperatures have on both overheating and condensing boiler efficiency, boiler system temperatures were included in long-term monitoring. We also tracked boiler cycling behavior at 13 of the 17 sites. This was important both because of the direct impact that severe short cycling can have on boiler system efficiency, and because of the impact that short cycling reduction can have on perceived value among boiler industry contacts. Reducing short cycling does reduce wear on some boiler components and provide some efficiency improvement. It also appears that highlighting examples of solving short cycling problems can be a powerful tool in marketing the boiler control tune-up service. Lastly, the most critical monitoring that we did was directly measuring natural gas savings. While the temperature and cycling monitoring were useful for understanding how savings is achieved and for telling the story to trade allies and customers, the real utility program value is in the energy savings. Gas meters were used to measure energy use and savings at 11 of the sites, and most of these gas meters included other gas uses at the site, such as service water heating. At 6 of the sites, the gas use and savings was monitored by tracking the individual boiler firing rates with data from the building automation systems. This approach ended up being problematic at a number of the sites, the approach of using the firing rate data, because of a late recognition that some of the sites had a nomenclature of reporting a 0% firing rate when the boiler was actually on and firing at its minimum rate. Separate boiler cycling data allowed for correction of much of this data, but not all of it. The long-term monitor data was compiled into daily averages, and savings was to be analyzed by comparing pre-tune-up gas use regressions against outdoor temperature to similar post-tune-up regressions, with typical meteorological year data being applied to determine annual gas savings. While this was possible at the 6 multifamily sites, the schools went through pandemic response shutdowns and restarts with different usage patterns, starting within a month of when the control tune-ups were carried out. Therefore, at the school sites, we generally estimated savings by comparing the limited amount and outdoor temperature range of post-tune-up data to regressions of pre-tune-up data. And the percent savings was then applied to the estimated annual use that was determined from the pre-tune-up models for the school sites. The last of the how issues are evaluations of cost effectiveness and program impact. Our evaluation of cost effectiveness used the costs that contractors billed to CE to carry out the controls tune-ups as part of separate site visits on a time and materials basis. Then user savings was evaluated using a natural gas rate of $7.60 per MCF, and program cost effectiveness was evaluated using inputs consistent with the 2021 to 2023 SIP program filings for the 3 largest natural gas utilities in Minnesota. Full-scale boiler controls tune-up program potential was evaluated using 2 independent approaches to estimate participation. The first was based on the count of boilers from the state's boiler and pressure vessel inspection list and assumptions about percent participation each year. And the second was based on assuming the same number of participants as existing boiler controls tune-up programs, which is what contractors told us they expected to be able to achieve. That concludes the summary of the how and who answers. Now I'll go over what we learned from the field trial of this boiler controls tune-up program or protocol. First of all, I'll highlight some key takeaways about the practical application of the controls tune-up protocol. We found that even after developing we thought was a fairly self-explanatory detailed form and supporting reference materials, a high degree of contractor technician training, coaching, and technical support were still needed, especially at the first few sites for each technician. Next, we found that every site had some level of temperature setting reduction called for in order to reach the typical ideal temperature settings for the type of building. However, nearly 1/4 of the sites needed to have follow-up temperature setting fine-tuning adjustments made to increase temperature settings within the first month. We also noticed that the sites with the most dramatic initial changes in boiler temperature settings tended to eventually backtrack on those changes within the first year following the tune-up. We'll have more on that later on. Using the protocol, technicians also found issues beyond simple control settings at about 1/3 of the sites, and most of these were able to be resolved during the initial controls tune-up visit. These issues included such things as temperature sensor problems and individual boilers being on manual control instead of automatically controlled by the main controller, or there being confusion between the BAS and local controller. The last 3 key takeaways regarding the application of the protocol are that at 11 sites with building automation systems, the temperature set point changes were able to be made without bringing in a controls contractor as a third party. Researchers were initially concerned about the inability of building staff or contractor technicians to change BAS set points, and that could be a significant complication and cost adder when conducting these control tune-ups in many buildings. But at least among the 11 school buildings that had building automation systems in the study, we didn't find that to be the case. We were able to make the adjustments during the single site visit. We also found that looking at mechanical plans was important to determine the target boiler system temperature for new HVAC systems that were designed for use with condensing boilers. And lastly, that the controls tune-up cost was around $750 per site. The sites averaging 3 boilers per site, this is only about $250 per boiler on average. Now we'll move on to the impact of the boiler control tune-ups on boiler system operation. The average system temperatures are shown in the graph at representative outdoor temperatures of 25 degrees and 50 degrees. The blue bars show the average pre-tune-up temperatures, and the red bars represent the average boiler system temperature after the tune-ups and any initial fine-tuning that was done within the first month. The control tune-ups initially reduced boiler system temperatures by about 12 degrees. While the gold bars, which show the average boiler system temperature at the end of 13 months of monitoring, showed that that backtracks in some of the settings led to net average reductions of about 5 degrees going into the second year of operation after the tune-ups. The site-to-site differences in system temperature reduction and persistence of those reductions were dramatic. Sites tended to either maintain all of their temperature reduction over time or to have temperature settings return to very, very near their original settings. None of the sites really made moderate changes or were only part way back toward the pre-tune-up set points. We also found that correcting staging control problems was critical to reducing heating season average boiler supply temperatures at 2 of the sites. Now we'll look at the impact of the boiler control tune-ups on boiler cycling. This next chart shows that the pre and post tune-up cycling rates for the 13 sites where it was available. Pre-tune-up boiler short cycling was at or above the 2 cycles per run hour level of concern for nearly half of the boiler systems. And the control tune-ups were very effective at reducing short cycling. The median reduction at cycling rate was 48%, and among the 8 sites that had pre-tune-up short cycling at levels of concern, the median reduction was even higher at 58%. Unlike the temperature setting changes, all of the staging control changes made during the control tune-ups persisted over the entire post-tune-up monitoring period of 13 months. Finally, the most critical item evaluated was gas savings. Rank savings for individual sites is shown in the chart. Note that the sites with the M in the label are multifamily buildings, and those with an S in the site label are schools, which had somewhat less reliable savings estimates because of the limited data caused by pandemic response shutdowns. Well, 1/3 of the sites had increased gas use or savings of 1% or less. 2/3 of the sites had first-year savings of 6% or more, which is far above the typical assumptions for burner tune-ups. Sites S3 on the far left and S1 were very similar in terms of the systems and boiler control changes. And the reasons for the differences between those 2 sites, including the one having the largest negative savings shown here, was not clear. Also know that the increased use at site M6 appears to be due to a follow-up site tuning adjustment made by a technician that was not familiar with the controls tune-up protocol and made some settings that would not have been setting changes that wouldn't have been called for by the protocol and the fine-tuning direction. Overall, the 15 sites that ended up with a good quality representative measurement of observed savings achieved an average savings of 7.7% and a median savings of 7.1%. It appeared that building type was a key characteristic that played the most major role in the amount of savings achieved at the various sites. Here's a summary of the results by building type for the 15 buildings with representative savings. This shows that the observed percent savings for multifamily buildings was roughly double the percent savings for schools. However, because the school buildings tended to have higher gas use to begin with, the magnitude of gas savings per site was actually larger for the school sites. Another key issue for turn-up services is the persistence of savings. We saw an overall average of 60% of savings persisted in the second year, and this is based on how the temperature settings backtrack compared to the initial tune-up settings. And so whether or not these savings persisted tended to be close to an all or nothing situation when looking at the individual sites, kind of like the differences between perennials and annuals. As I said before, both sites either maintained their settings where they were at, or they went all the way back to where they were before. There really wasn't much of a partial backtracking, especially for setting changes that were made after that initial adjustment period. While setting changes in response to underheating was a major concern that researchers had going in, we found that other factors also often contributed to the failure of the savings to persist at some sites. Other issues that have apparently impacted more than one site included whole building automation system reset to previous defaults, and on-site operator misunderstandings regarding things like the intent for control of temperature via BAS control setting or the local controller, or the use of automatic outdoor reset versus doing manual adjustments during seasonal changes. This next chart highlights some of the key correlations that we found between the amount of boiler system temperature reduction, first-year savings, and persistence over time. Across the horizontal axis, the data is grouped together into ranges of initial reduction in boiler system temperature, with a little jumping between ranges due to the steps between the actual data and the limited sample of buildings. The groups each have about the same number of buildings in them, and they are less than those with changes in temperature of less than 8 degrees. Those with changes in the 8 to 10 degrees is the second bar. And then there's groups with changes from 12 to 17 degrees in the third blue bar. And finally, changes in boiler system temperature reduction of 21 to 25 degrees in the last bar. The blue bars show the average first-year savings with the scale on the left-hand side, while the red line shows the average persistence into the second year with its scale on the right-hand side. It expected the blue bars to show savings increasing as the temperature reduction went up, but didn't really expect to see the big stepwise and apparent plateau going from the 8 to 10 degree range up to the 12 to 17 degree range. And then that didn't seem to increase as the temperature reduction went up beyond 20 degrees. Unfortunately, we also saw that the average persistence of savings into the second year went down as the amount of temperature reduction and first-year savings went up. It appears from this data set that the sweet spot for an optimal combination of first-year savings and long-term persistence occurred in buildings that had a temperature reduction between 12 and 17 degrees, as was called for by the protocol. Although it wasn't completely clear how much of this trend was due to actual underheating issues versus the other issues that I described before, this finding did lead us to update the protocol to limit initial control tune-up changes to no more than 20 degrees below the as found pre-tune-up settings. And we're hoping that that will keep the savings about the same and increase the persistence over time. Now we're going to take a step back from the details of the technical results for a high-level summary of the cost effectiveness and potential program impact. First of all, the median simple payback was about 9 months, or 0.73 years, and 10 of the 17 sites had a simple payback of less than 1 year. Also, the high-level result is that the combined achievable program potential for the 3 largest investor-owned utilities in Minnesota was estimated at nearly 200 decatherms, which would represent about 10% of the current commercial and industrial saving SIP program portfolio savings. The cost effectiveness results from a program level are summarized here based on incentives covering half of the service cost and using the first full year savings over an assumed 2-year measure life, as is done for traditional boiler tune-ups that focus on burner adjustments. The first plot is also based on the same ratio of program to incentive costs as large Minnesota gas utilities used in their 2021 to 2023 SIP filing. It shows estimated societal benefit to cost ratios of 1.4 or 1.74, depending on whether the mean or median savings and cost values are assumed. The gas utility cost effectiveness ratios are similar at 1.34 to 1.67. This next graph assumes a 25% higher program cost to account for a higher level of program-specific protocol, reference material preparation, contractor technician training, on-call technical support, and quality control, which are all needed at a higher level than what is done for burner tune-up programs. Even with these higher program costs, the societal benefit to cost ratios are estimated at 1.3 to 1.6, and utility benefit to cost ratios are estimated at 1.2 to 1.5. The last thing I'd like to do before opening up for questions is to summarize our SIP program recommendations based on the study findings. First group of recommendations is centered around SIP program development and marketing issues. Because we generally found more enthusiasm among service contractors than among end users, we recommend additional end user focused market research to better understand the best name for this new service and the best messaging and marketing approaches, as well as the realistic achievable potential participation. Secondly, program planning should allow for a slower startup and a higher program cost budget associated with the detailed training, technical support, and QC activities. Thirdly, because the marketing and implementation success for this complex service will depend greatly on the buy-in of contractors, it's critical to include contractors during early program planning to ensure that the program is set up in a way that works well for them. If the program does work well for contractors, the fourth recommendation of leveraging boiler service contractors as a primary means to promote the controls cleanup service will come easy. Because if it works well for them, then they're going to be promoting it. The close relationship and trusting relationship between service contractors and customers regarding such detailed technical things as their boiler controls is hard for utility staff to match in their conversations. Lastly, we recommend that utilities try out different approaches to try and maximize the persistence of savings over time, as that's a key issue for this service. Finally, the last set of SIP program recommendations is focused on implementation issues. First two implementation recommendations are providing extensive program-specific contractor training and on-demand technical support, and instituting a robust quality control program will require a higher level of program involvement than is typical of current boiler tune-up programs that are focused on burner adjustments. The third recommendation is to be sure that certain expectations are clearly communicated to customers ahead of the control tune-up site visits. Being sure that a staff person with the BES set point access and the ability to change that set point, and that mechanical plans will be available for review at the time of site visit, will be critical to achieving the energy savings without having to make repeat site visits at additional cost. Lastly, having a system that requires the technician to have a degree of familiarity with the application of the controls tune-up protocol for each site's specific make and model of controller will greatly improve the effectiveness and savings and reduce the amount of on-call technical support that might be needed. That concludes the prepared remarks that I had, and with that, I'll hand it over to Laura.
Yeah, thanks, Russ, for that great presentation. If you've not already done so, please type any additional questions into the Q&A panel and send them to all panelists. Laura, do you have any questions for us at this point?
Yeah, I'll start off with a few questions about the project design. First, were there any commercial real estate buildings or facilities included in the study?
No, they were not in this study, and that the targeting was based on the population of condensing boilers that we saw in the state boiler and pressure vessel database, and it seemed like school buildings were far ahead in terms of the percent of buildings with condensing boilers, and even though most of the protocol can be applied to non-condensing boilers, we expected there to be a little bit higher level of savings with condensing boilers. So we focused on those for the study itself. but we do expect that this could be applied comparably with similar savings to probably to what we had seen in the school sites at other commercial buildings.
All right. What was the BTU per hour size range of the condensing boilers that were studied in the project?
I think the final report has a lot more detail on this, but off the cuff, I'd say that the minimum size was about 200,000 BTU per hour per boiler, and that was in a multiple boiler system. Again, and it had 3 or 4 boilers in systems with the size that low, but more of the boilers were in much larger ranges. There was a few that were below 1 million BTU per hour each, and a number that were in the more 1 to 3 million BTU per hour each, and the highest size was either 3 or 4 million BTU per hour. And can get back either with a fuller response to that offline afterwards, or that's also will be available in the final report.
Okay, great. And then another clarifying question. When you were talking about controllers, we said when you say controllers, are you talking about energy management systems or something else? And I noticed that this came up talking about what we learned section. Go ahead.
Okay. Yeah. And what I was talking about the controllers, I'm referring to the local controllers in the boiler room, and often those are actually built into the boilers. And the more modern boilers will have each boiler will have a control system that's capable of controlling multiple boilers. So in general, it's kind of the local controller that's handling the staging of the individual boilers. And in the buildings where there were building automation systems, they just passed a temperature set point to that local controller, and then that local controller dealt with the with the control of the individual boilers.
Great, thank you. In your analysis section during that time, somebody asked, do you have an estimate of how many trade partners currently sell these types of boilers that you? How many different partners, or I guess manufacturers or contractors? What does that look like?
Well, we targeted 3 or 4 specific manufacturers of boilers that were the most common. Because of the variations in controls between the manufacturers and how they're programmed and everything, we started with that target, but we ended up applying it to a number of boilers that were not within that target range. So there's I don't know if that's a direct answer to that question, but we're looking at a variety of the most common boilers in Minnesota. And the general concept can be applied, and our protocol is kind of developed in a general sense, but then we have reference materials that provide more detail for specific makes of controllers.
All right. Now a couple questions. Well, I guess this is also came up during the analysis portion. When you when you were talking about the potential, this came up when you had the slide about the potential for this program and comparing it to the current statewide portfolio. So the question is the potential broken out by utility service territory, or is it lumped together at a state level?
We in the report, that's just lumped together at a state level. But I think it's I think using the information from the report, the utility that has their information in terms of what their could a utility that knows their information on their participation level could probably use that information to break that out for their utility service territory, and we'd be happy to work with someone to help them figure that out.
All right. Question is, did sites give a reason for undoing the set point changes?
In some cases they did. In a lot of cases we got, we're talking to them on the phone, but we got the equivalent of a deer in the headlights stare when you're asking about what happened and why it was changed. And a lot of times they just, there was no explanation. So in many of the cases, so that's why, I mean, and we know when there was one school district that had this setup of, and the building automation systems, operators could do overrides, but they were labeled as overrides, and they could not make changes to the default settings for the boiler controls. And that was something that would take special action by someone at the district level. And in that case, I think doing that follow-up to make sure that those defaults were changed might have led to greater persistence. But it's we suspect that there was just kind of like a system-wide reset of things back to the defaults, because nobody had any recollection of there being changes or them having any problems that would have led them to make changes to the control settings. So in some of these, there was, I think I didn't emphasize it very much, but there was 4 of the sites where early on there was fine-tuning adjustments made, and in general those were all because there was underheating of spaces, and then they reached out either to us or the contractor, and then we worked with them to make some fine-tuning adjustments that that allowed for most of the savings to be kept. But in a lot of the cases where things were just set differently at the end of 13 months, unfortunately, we weren't able to fully understand that, and I think that's on a wider level, there's going to be different variations in terms of why and how changes are made over time. And it kind of the flip side of that is that's some of those things that have happened over time is what provides the potential for the savings from this optimization service.
All right. Another question about controls, I guess, is the question is, I'm very discouraged with my support from a very large local vendor working with my BAS. How can we know the vendor is qualified? What if the vendor maintains proprietary control over the BAS?
I think a lot of that gets into issues beyond the boiler the boiler controls. But what we found is that most of the building automation systems are, in terms of how they define the boiler outdoor reset controls, that they're pretty consistent in using set points and a curve that looked very much like the that curve that I had on the slide, and they have fairly consistent definitions of how that's set up. But in terms of vetting a controls provider, I think I know that's can be a very tricky issue with a lot of facets to it, and that's not something that we dealt with on a high degree for this project. It's something that I'd say some of our engineering staff that's done more recommissioning work would maybe be able to address that better. And that's something that state staff may have some comments on.
Okay. A couple, I'm going to combine 2 questions that have to do with persistence and training. So do you have a recommended trainer for training on trade in these new tune-ups, and then thoughts on savings persistence. Thoughts on if savings persistence will improve in year 2 if site training and education increases.
I think I'll focus on the second question there, because in terms of anyone that's done this before, I mean, just what we've done as part of this project is really kind of the main the main experience with doing this as part of trying to develop a utility program. So it's I know that there are a lot of manufacturers that have some good training programs, but in terms of providing a broad training on this program and the protocol itself, there isn't, other than what the researchers have done. I can't point to anyone that really is provided with that focus. But then in terms of sorry, can you repeat the second part of the question? I know I had a lot more to say about it.
Do you have it? Would that be? Do you have an
estimate? I think
sorry. No.
Yeah, I remember now. It was
recommendation on training.
Yeah, I was dealing with whether doing more with on-site could improve the persistence. Yes, and that's one of the options that I talked about in the recommendations for program planning is kind of to develop and test different ways to try to improve persistence over time, and that's one avenue that definitely could be done. In the as this protocol was applied, it was for this field study, we didn't emphasize that very highly. We emphasized more working with the contractors and through the contractors. And at the time that the boiler tune-ups were done, for most of the sites, there was just like a one-page leave behind that was left at the site that noted that this change was done, and it documented exactly what control change was made, and that this was done as part of a study. And if there's any issues with that they should either reach out to the contractor or the researchers and work through us to have a recommendation in terms of how the things can be fine-tuned to deal with any issues that they were having. But that it was definitely variable in terms of whether things happen that way or not. I'd say So I think there is a lot of area for developing and improving the services and the persistence through different approaches like that, of working more closely with the site operators.
Great. And I'll note there were a couple other questions about persistence and more details on that. Request for more details and will that be looked at further? So I think I think your response kind of covers. There's a lot of potential to keep looking at that in more detail.
And also I'd like to point out that we intend to for the sites that where there was persistence into the second year, we intend to circle back to those. Even though the project is formally done, we intend to circle back with those after at the point of 2 years after the initial tune-up or later, and then have some updated prepare some kind of updated summary in terms of how much that persistence went through the second year and beyond. And that's something that if you follow up with us in another 9 months or so, and we can give you an update on that.
Great. So there are a few more questions. I'll give you one final question, then we can turn it over to Mary Sue after this to close out the session. So question is, was there an efficiency size range for these boilers that utilities should look at making prescriptive versus custom?
I think our recommendation would be that this should be this should be developed as a prescriptive program, as we always envision this to be something that happens alongside of the burner tune-ups, and then having it be custom it just adds so much to the cost and the effort and the, for it to be custom, you really kind of need to look at it ahead of time, determine what you're going to do, and then circle back later to do the changes. And it's just from a program implementation standpoint and efficiency, we just felt like having the technician, when they're out there doing a burner tune-up, also go and look at the controls and do what they can during a single site visit. Is the most overall cost-efficient way to deliver this savings and achieve this savings at as many sites as possible.
Okay. And I know I said that was the last question, but since you were just talking about a good way to deliver these measures, there was one clarifying question somebody had. Did contractors do regular boiler tune-ups in addition to the advanced boiler tune-up? Or was this just the latter? So I think that was looking for clarification about project design.
Yeah, for this study design, we avoided doing burner tune-ups at the same time so that we could isolate the savings from just the control tune-up portion. But there did happen to be, and we asked all the participants to not have burner tune-ups done during the time period, but there was one school district that did have burner tune-ups done at some of the sites, and it turned out that their percentage change in the efficiency from the burner tune-ups was very small compared to the differences we were seeing from the control tune-ups. They were I don't want to close, but most of them, they were less than a percentage point change, and some of those actually had the efficiency go down instead of going up. But it is generally much smaller impact than what we were seeing from the controls.
Okay. Well, thank you, Russ, for those questions. And Mary Sue, why don't you give us your closing remarks?
Great. Thanks, Laura. And thanks for helping us out today. If you have any follow-up questions about this card project, feel free to contact Russ or myself. A recording of this webinar and slide set will be available on the department's website in a few weeks, and the final report in a couple of months. When available, you can link to either of these from the quick links on our Applied Research and Development webpage, as indicated on this slide. The CARD R&D webpage has additional resources and information related to the CARD program and to CARD research projects, which you can check out by going to the address at the bottom of this slide. Thanks for participating today. We appreciate your interest in CARD projects. And before I leave, I want to take this opportunity to mention another upcoming CARD webinar on October 19th, 2021. The Center for Energy and the Environment will be back to discuss results from an assessment of opportunities for state-of-the-art high-performance envelope retrofits on existing single-family homes. Laura will be there as well, since she was the project manager on that one. But in the meantime, you can keep abreast of upcoming webinars and other news related to the Minnesota Conservation Improvement Program by signing up for SIP updates on our email list. You can do this using the link on this slide. In the meantime, feel free to contact me if you have questions or suggestions for the CARD program or for the webinar series. And as a final reminder, there will be a short evaluation that launches after the webinar. Please take a few minutes. We'd really appreciate it to fill it out and let us know how we did. Thanks so much for joining us today, and I hope you have a really good rest of your day.